Okay, so today we're going to be talking about the morphological aspects of natural language processing. And by morphology, this is a word that can mean more than one thing, depending on the domain that you're talking about it in. So if you've studied biology, what is morphology? Anybody had a biology class ever? So what does morph mean? Not the newish meaning of changing shape, which is totally wrong. But what does it mean?
The shape of something.
The shape or the form of something. So like amorphous is without shape. Morphology is about the shape of things. And when we use it in linguistics and natural language processing, we're talking specifically about the shapes of words, the forms of words, and more specifically about the internal structure of words. So one complaint that we sometimes get in this course is that there's too much linguistics. So the book, you'll notice, has a lot of linguistics. And I have a lot of linguistics in me, too. And sometimes people say things like, I'm not a linguist, I'm a computer scientist. Why are you talking to me about linguistics? But NLP is not just P. It's also NL. And just as if you're studying biology or computational biology, you'd need to know something about biology. In order to study natural language processing, it's really helpful to know something about language and how language is different as a problem than other problem domains. And it can be really helpful. And so we're going to talk about some linguistics today. We're specifically going to talk about words. Now, words are not atoms. By that I mean that words have internal structure. I don't mean atoms in the sense of real atoms, because we know they have internal structure, right? But atoms in the classical Greek sense of these indivisible particles. Words are not like that. They're composed of what we call morphemes, which are meaningful units. You can forget this pretty easily if you're a speaker of English or Chinese, because English and Chinese are morphologically impoverished languages. They're languages with very little, where a lot of words are just one morpheme long. And when you do put morphemes together, it's to make compound words. But even in English and Chinese, then there's some other kinds of morphology. So in English, you can have words with like a few morphemes, like misunderstandings. Each of these parts has a meaning to it, and it occurs in multiple different words, and it does something. You can also, there's also in Chinese even this morpheme man that occurs in like 我们 or 他们 or 你们, which are pronouns, but it can also occur in some other words like 同志们, which literally means comrades, although I understand that it has another meaning. So there are different kinds of morphemes. There are roots. These are like the centers of words. They carry the main part of the meaning of the word. And then there are affixes. And these attach to the root to form stems and to form larger words. And affixes can be divided into basically four types. There are prefixes that come before the stem. At the beginning of the stem, there are suffixes that occur at the end of the stem. There are infixes that occur inside of the stem. And you might think, in English, this doesn't happen very much. There are this marginal case called expletive infixation, which is like pencil frickin' vania or California, or New Mexico bloody co. But in some languages, this is really important. So like in Tagalog. Does anybody here know where Tagalog is spoken? The Philippines, yeah. So Tagalog uses, and a lot of related languages use infixation extensively in their grammar. So you can't do anything grammatically in Tagalog without dealing with infixes. And then there are circumfixes where you stick something on either side of the stem, like in German gesammelt, where you put a g at the beginning and a t at the end to make the past participle. But there are also ways of doing morphology that don't involve concatenating stuff. I mean, infixation doesn't involve concatenating stuff, but there are things like umlaut, which we have in English. So you have foot is to feet, as tooth is to teeth, as dog is to dogs. So you're forming the plural by changing the vowel. So that's kind of umlaut. We also have a kind of vowel changing morphology called ablaut. Not in very many verbs, but in some you have things like sing, sang, and sung, where you form the different inflectional categories of the verb by changing the vowel. And this gets taken to a crazy degree by Semitic languages like Hebrew and Arabic, where they have what's called root and pattern morphology, where roots are just like 2 or 3 consonants. And in order to form different words from those roots, then you shove vowels in between them violently. It's the source of Middle Eastern conflict, all of the violent shoving of vowels into consonantal roots. Then you have infixation, which we've already talked about. So graduate in Tagalog has as one of its forms grumadwet, where the is getting infixed to mark grammatical information. So those are like formal differences in kinds of morphology, but that you have to deal with. But there are also functional differences that can be very important in making NLP kinds of decisions. The main division here is between inflectional morphology and derivational morphology. So inflectional morphology just adds information to a word. It makes a new form of the same word that is suitable for a particular syntactic context. So it goes in a particular place in a phrase or in a sentence, or it carries information like plurality. These are all inflectional categories. So like case or number, and often you want to get rid of inflection. So there's this task called lemmatization, which is basically the process of taking all of the different inflected forms of a word and mapping them to a single dictionary form of the word. Because inflection makes the same word look like a bunch of different words. And we often don't want that, particularly, well, when wouldn't we want that? When would that be disadvantageous to us, to have inflection on our words? Yeah?
But for the same words, you probably classify them as different words, and you won't get the same meaning.
Yeah. If your model treats them as different words, then you might run into some problems, even though they're the same word. They just look different, right? So what kinds of tasks might be complicated by that? Yeah.
For example, if you maybe a search engine or something, and if the person searches for automata, then we want automata there as well. So we can't treat them as
Right. So information retrieval relies heavily on stemming and lemmatization. Getting rid of that inflection or getting rid of inflectional differences. So that's one example. There are other examples we could talk about too. So derivational morphology actually creates new words with new meanings, and often having new parts of speech. So if you take parse and make it into a parser, that's derivation. Or if you take repulse and make it into repulsive, that's also derivation. Now, one problem with morphology is that it's not very regular. This is the big problem with morphology, actually. It's the thing about morphology that's not beautiful. The one thing about morphology I do not love. Sometimes inflectional markings differ depending on what root or base you attach them to. So you have walk is to walked, as sing is to sang, is to sung. So this is a kind of formal irregularity, or doing something different to accomplish the same end. Can be a problem. There's also semantic irregularity or unpredictability. So for a derivational morpheme, often the same morpheme will have different meanings in different contexts. So you can say a kindly old man, or the old man was kind. And you can say the old man was slow, but you can't say a slowly old man. So there's an irregularity in the meaning of this ly suffix. So morphology can be both good and bad from the standpoint of an NLP engineer. Inflectional morphology often gets in the way, as we've discussed, and so we often want to get rid of it. We want to stem it away or do lemmatization, which is something I've worked on in minority languages. Morphology, however, also encodes useful information, or information that can be useful in NLP tasks. Things like machine translation, or natural language understanding, or semantic role labeling. It contains information about the meaning of words that can be leveraged as well. So morphology has its good and bad sides. In NLP, you might say that morphology is largely a solved problem if you're willing to work with a rule-based solution. If you're trying to do machine learning and handle morphology, then it's still wide open, and we'll talk a little bit about some of that. But for a lot of morphology where there are a lot of, it's a very knowledge-oriented kind of task, then these rule-based solutions actually work pretty well. And they're based on finite state methods. This is what Google, for example, uses to do their morphology. They use massive numbers of finite state transducers. So let's define the problem a little bit. The problem in doing morphology is basically getting from one representation to another. Often, we start off with the orthographic form or surface form of words here at the bottom. And what we want is something more like a lexical form. So we want a lemma and some set of inflectional features. Those are what the things with pluses by them are. So that's morphological parsing or morphological analysis. Sometimes, however, we want to do generation. We want to go the other way. And the cool thing about finite state technologies is they allow us to go both ways with the same code, which I think is very cool. You should think it's very cool. If you don't, I just don't know about you. So how are we going to do this? We're going to do it with finite state transducers. And what these do is define regular relations between strings. In practice, these are widely used, not just for morphology, but also in speech, in surface syntactic parsing, and other applications. And another great thing about them, besides the fact that they're reversible, is that once they're compiled, they run in linear time proportionate to the length of the input. So that's much more efficient than most of the other approaches to the same set of problems. I mean, it's not constant time, but it's linear time. Yeah, anyway, to understand FSTs, though, we first have to understand their simpler relative, the finite state automaton or the finite state machine. Who here is familiar with finite state machines? Hopefully a lot of you from theoretical computer science classes or formal language and automata classes. Who here likes finite state automata? I found my people. So basically, you can write finite state automata to tell you whether a word is well formed or not, but they can't actually do analysis and generation. To do that, we have to take things another step. So finite state automata are simple creatures. They have a finite set of states, Q, a special start state, a set of final states, and we usually write the final states with a double line. A finite alphabet, sigma, and then they have transitions between states. And each transition has a label that's drawn from the alphabet. By the way, pet peeve of mine. Is A an alphabet? No, A is not an alphabet. A through Z is an alphabet. A is a letter or a character, but it is not an alphabet. An alphabet is a set, and A is a member of that set. Anyway, and so we're talking about a set here, right? So basically, this encodes a set of strings. A finite state machine corresponds to a set of strings that can be recognized by following the paths from Q sub 0 to some final state. So here's an example of an FSA, finite state automaton. What are some examples of strings that are encoded by this FSA? Yes? Okay, the one in the title is an example. So what is a similar string that is not encoded? Yes? BA exclamation point. Why? So you can go here, you start here, BA exclamation point, right? No, so you're stuck here. It's not a final state. You have no way of getting to to this transition with an exclamation point without going over here. It's very bad. So that string is not in the language defined by this beautiful finite state automaton. Any questions about that? About FSAs, FSMs? Do you all get this? So you have to eat up all of the letters on the input tape, all of the characters, the symbols on the input tape, and you have to end up on a state that has a double circle, on a final state. And if you do that, that string is in the language. And if you don't do that, the string is not in the language. So don't let me lead you astray, though. So when we talk about this, we often, we trace our way through, and you can get the idea that this is about an algorithm for finding one's way through the machine, through the network, through the graph, and there's a right way through the graph. that's not really how it works. What we're really saying is that, you know, a string is in the language if there exists a path through the network where that string is consumed. I'll skip that. So the set of languages that can be defined by finite state automata is called the regular languages. Why is this? Well, you don't have to answer that. But does this ring any bells? Regular languages. What else is regular? Regular expressions. And why would these things go together? Because regular expressions, real regular expressions, not like Python or Perl regular expressions, which are like regular expressions plus, because they have back references. But real regular expressions and finite state automata describe exactly the same set of languages, encode exactly the same set of languages. So you can do this, use finite state automata for English morphology. And for morphology of any language, to build a recognizer that will say whether a word is in the language or not in the language. And this is where you say reg noun and irreg plural noun and plural s. So these actually stand for a whole set of transitions and even states. But this is a shorthand to make things understandable. So, you know, regular nouns that are pluralized with s can make it to a final state. Regular nouns that are not pluralized can make it to a final state. Irregular plural nouns can make it to a final state, and irregular singular nouns can make it to a final state. So, you know, that shows basically how you can construct an FSA for English nouns. And similarly, we can do this for English adjectives. In fact, we can go and do the same thing for all of the derivational morphology of English, at least a fragment of the derivational morphology of English. And you end up with something like this. So you have different verb classes, verbs of J, verbs of K, different noun classes, nouns of I, nouns of L. And they, you know, if you're in that class, if you're one of the stems that are in that class, then you go to particular transitions, and you know, these are all suffixes, and so that makes it a little bit easier. If you had to do the prefixes, then you would need to do it a little bit differently. Let's talk though about the real issue here, and that is finite state transducers. Let's go back to this slide. So let's say you want to get from here to here. You want to get from foxes to the set of parses of fox that are allowed in English. It could be a plural noun or a singular verb. Let's say out foxes. So you might actually want to go through an intermediate form where you took where you had all of the morphemes separated by a caret, and you marked the end of the word with a hash mark. And this would make it easier to then go here. So you break it up into steps. And so this intermediate form is sometimes called morphemic form as opposed to the lexical form and orthographic form. And what finite state transducers are going to allow us to do is to write transducers that map from the orthographic form to the morphemic form, from the morphemic form to the lexical form, and then we can combine those together through the operation composition and get a single transducer that will take us from orthographic form to surface form, Then, in the tour de force, we will reverse the order of that application of that transducer, and then we can go from the lexical form to the orthographic form. And then we rest. So if we wanted to do this task, though, there are three options that we can think of for going from orthographic form to lexical form. You can probably think of additional options than this. So what about a table, like a lookup table? What advantages would this have? Yes?
Probably really fast.
Be really fast. Really fast. What disadvantages would it have?
Really large.
What?
Really large.
It had to be really large. So there's a storage disadvantage. What else? Yeah.
I don't know if it could handle new words.
Yeah, what would it do with new words?
Just forget them.
You just say nothing about, you have nothing to say about out of vocabulary words. Because you can't do anything, it can't capture any kind of generalization. It's just a dumb mapping. So it's fast, but it has some limitations. What about a try? What advantages would it have over a table?
Save memory.
Yeah, it would be less memory intensive. What disadvantages would it have? What disadvantages would it share with the table?
More time to
The what?
search. More time to search.
Okay, so it would be slower than a table. The time efficiency would be less.
You don't solve the vocabulary problem.
Yeah, you don't solve the out of vocabulary problem. So finite state transducers are not as fast as a lookup table, but they can be fairly large, but they're not necessarily much larger than a try. And they there are actually ways of solving the out of vocabulary problem, of dealing with out of vocabulary words and providing meaningful morphological parses of them. So finite state transducers are a lot like finite state automata, in that you have a finite set of states, a special start state, Q sub 0, a set of final states in F, and then instead of having one alphabet, you have two alphabets, sigma and delta. And instead of having on your transitions one symbol, you have two symbols. We often separate them with a colon. One on the upper side and one on the lower side. Or one on the input side and one on the output side. And you imagine having two tapes that you're reading and writing from and to while you're going through a finite state transducer. And you read from the input tape. And when you go through a transition, you read this from the input tape and you write that to the output tape. So why do we need this? Well, let's take the example of Turkish. Turkish, as you may know, anybody here speak Turkish? Good. Because Turkish is a terrible language. You have words like this. No, it's a lovely language, but you can have really long words that have lots of morphemes in them, and it's all predictable. Turkish morphology is actually very regular. So you can make these words that are basically whole sentences in English. Uyghurlaştı amadıklarınızdan gatsina. Behaving as if you're among those who we were not able to civilize So you're not likely to come across this word more than once in a corpus. But it would be nice if your system didn't fail every time it saw a word like this. Well, FSTs have the solution to that problem. So rather than doing just listing all of the different words, we can actually parse the words into their parts and just essentially list the parts. So here we had the finite state automaton for English nominal inflection. Here we do something similar with a finite state transducer. So we have all the transitions for regular nouns, irregular singular nouns, irregular plural nouns, and then we read nothing. Epsilon here means nothing, the empty string, from the input tape, and we write plus n to the output tape because we know it's a noun. Same here for irregular singular nouns, irregular plural nouns. And then if it ends in an S, if it has a morpheme boundary and then an S, then we write plus plural. If we just have a word boundary, if it's just at the end of a word, and this is operating on the morphemic representation to give us the lexical representation. So there we have these plus, or these carets and hash marks. Then this gets us to our final state. So we know that that mapping between that regular noun, let's say plus S, is in the relation that corresponds to this finite state transducer. Questions? This is probably a little confusing, but you're going to have a homework on this. So if you're going to ask questions, you might as well ask them now. Actually, I mean, I copied this from the textbook, and I think it makes it a little bit confusing, the way that he uses these labels for whole sets of transitions rather than just the one, and shows it just as one transition. You know, so you kind of don't always get the right idea of what he means. But let's go further. So one problem here is what is called morphotactics. And it's the problem of how you relate the order of morphemes to the order of these of lemma and features. How you relate these things to each other, and what order the morphemes come in. So that is captured by, that can be captured by finite state transducer, and that's often done with the finite state transducer that goes between the morphemic level and the lexical level. It takes care of what's called morphotactics. But there are other things you have to deal with as well. So there are these spelling rules. And a lot of languages have these, where you change the spelling of a morpheme depending on its context. So, for example, some consonants are doubled before ing and before ing and ed. So you get beg, but begging. So you have to deal with that. If you're going to make this into, if you're going to go from the lemma beg to the orthographic form with the two G's. And you have similar problems with E deletion, E insertion, Y replacement, and K insertion. Well, you can represent these as FSTs as well. And here's an example of the E insertion rule as an FST. This is going between the morphemic level and the orthographic level. So let's go back to my favorite slide here. Okay, so the idea is at the orthographic level, that's just how we write it. The lexical level, you have a lemma, which is like the dictionary form of the word, and then a list of inflectional features. The intermediate or morphemic form has a sequence of morphemes, but these are normalized so that every morpheme has just one form. So for example, the plural S, even though it can be ES or S in English, it's always just S. And each of these is separated by a caret, and all of it is terminated by a hash mark. So this is what the morphemic form or intermediate form is. So morphotactic stuff maps between these two levels. We're concerned about the order of morphemes and how we map and how you put the morphemes together. So how you map between these features and this morphemic representation. These orthographic rules, these spelling rules, are modeled by the transducer that maps between these two levels, the morphemic level and the orthographic level. Does this make sense? Questions?
Excuse me, could you
Yeah.
please explain what Fox plus V plus ST means again?
Yeah. So Fox, you mean this?
No, the upper part.
Fox, so this means Fox, verb, singular. And this means Fox, noun, plural. So, this means this is a singular verb, Fox as a plural noun.
Okay.
And it can be either one of these. Foxes can be either one of those. Okay. So you can take FSTs and you can put them together to make bigger FSTs that do more magical things. And this is a process called composition. So we can take our lexicon FST that handles our morphotactic rules and our orthographic rules, this FST, which is probably actually a combination of other littler FSTs for each of the rules. You can take those and use them together. So here, we are essentially mapping the lexical form to the morphemic form and morphemic form to the orthographic form. But it's more efficient if we combine these into one FST, which we'll talk about in a moment. If you go this way, you're parsing. If you go this way, you're generating. So FSTs have neat properties. And one of the things is they're closed under a number of neat operations. When I say they're closed, I've had questions about this in the past, so this is why I asked. When I say closed under an operation, what does that mean? If FSTs are closed under an operation, yeah.
You perform that particular operation with an FST or two FSTs, then you get another FST.
Right. So they include intersection, union, concatenation, cleaning closure, and composition. And you can read the definitions of each of these. It will be useful to you to know, particularly intersection and union, maybe concatenation, but composition is the one that is most useful to you, and that urge you to make sure you understand. But it's pretty simple to understand. So if you have, as we've seen here before, so let's say you have a lexicon FST, handling our morphotactics. We have a bunch of different FSTs for each of the orthographic rules. We can then take the intersection of those rules and get an FST that does all of that. So now we've got lexicon FST and this orthographic FST. Well, then we can take and compose these, and we get just one big FST. Now, why would we want to do that? Well, it's computationally much more efficient for one thing. You know, it's basically, you know, since it's linear time relative to the, not to the size of the FST, but to the length of the input, then you're essentially cutting the time that it takes to run in half. So that's good. But it's just more elegant and more beautiful. And don't do it this way. Do it this way. On your homework, there'll be a homework, and like 25% of you will say, I just fed the output of network X of FST-A as the input of FST-B. Don't do that. Just say, I composed FST-A and FST-B. I got a new FST, FST-C. And it was beautiful, and we were all happy. And we went home and had a party. So, yes?
What does it mean to take a union of FST?
Good question. So if you can think of it, the easiest way to think of it is just in terms of relations. So as we mentioned before, every FST encodes a relation. You can think of it even as a set of tuples. The union of two FSTs, so each FST is a mapping relation. Then the new FST includes all of the mappings that were in either of those original FSTs, or that were encoded by those original FSTs. So it's just union in the set sense.
So the final state would be union.
So the final, you can't, it's a lot more complicated than that. So for all of these operations, there are algorithms that correspond to these operations that can give you the intersection of two FSTs or the union of two FSTs. But these are not trivial to understand in terms of just changing the graph in a particular way. These are algorithms that are not super complicated, but they're not things that you would want to do on paper. So if you're interested in this, there's a good book called, it's by Hopcroft and Ullman, called Automata and something with automata in it. Anyway, which has the algorithms for doing all of this. Hopcroft and Ullman. So we're not going to, like the actual algorithms for computing the intersection between two FSTs. It's not something we're going to cover or that you're expected to know. But if you're interested in it, then that's a good sign. So talk to me and I'll point you to some more information on it. Any other questions about operations on FSTs? Yeah.
Could you talk a little bit more about the closure?
About what?
Closure.
Closure?
Yeah.
Yeah. So, what about it?
The first one have listed on the 5.
Yeah.
Yeah.
Yeah. So, Kleene closure?
Yeah.
Okay. So, Kleene closure is a unary operation. So you take a transducer T and you get T star such that you have an empty string before and after T star. And I don't know how to explain this in an intuitive fashion. So it's like the Kleene star in regular expressions. It's probably the easiest way to understand it. I think that this will help. So, so it means that you can create for any finite state transducer, you can create a finite state transducer that's like the concatenation of, that accepts the concatenation of any number of it's like the Kleene star for finite state transducers, basically. So yeah.
Wouldn't that just be a loop?
Yeah. Yeah, that actually is pretty easy to see in terms of, yeah. You know, yeah, it's just a loop basically, so it's an easy operation on the network, on the graph. So Kleene closure is not something that we will talk about, so you don't necessarily need to know about it. It's just listed there for completeness, so you know these are the closure properties of FSTs. So here's another thing. So on the homework, inevitably we get a lot of questions that have to do with non-determinism. So finite state transducers can be non-deterministic. That means that you could have that a finite state transducer can define a many-to-many mapping between strings. Sometimes this is desirable. Sometimes it's less desirable. But people kind of get caught up. You know, they're like tracing their way through a network, and they see a case where they could take more than one path. And they want to know, which one do I take? Which one does it take? And the answer is you're looking at it wrong, because it's not about finding the right way through the network. It's asking, does there exist a path through the network that satisfies these criteria? So you don't think of it in an imperative sort of way. Think of it, who here had the class where you do standard ML? Or who here has programmed in Haskell before? Or who here has programmed in some language that is not imperative? It's either declarative or functional. So take off your C++ or Java or Python hats and put on your functional or declarative hats for a minute. And don't think of this in terms of steps that you follow in terms of computation and where do I go now. Think of it in terms of the whole problem of the function. Think of finite state transducers as just as relations, as a way of describing a relation, not as something that you compute your way through step by step. Does that make sense? This will be very valuable advice to you, if I do say so. Okay. Forgot what time we finished, so I had to look it up because I was too embarrassed to ask. Okay, so you can take a deterministic, a non-deterministic finite state transducer, and in some cases you can make an equivalent transducer that's deterministic. So a non-deterministic finite state transducer would be one, for example, where you had more than one transition out of a state that had the same label. So in a lot of cases, you can take such transducers and determinize them. Not true in all cases. There are algorithms that you can apply that tell you whether a finite state transducer is determinizable or not. But because of power set construction, you can't do this for all, because of the problems, the power set construction problem, then you can't do it for all FSTs. So morphology is one area where in actual practice you may want to use a rule-based solution. I'm biased on this. I work on a project where I have developed rule-based morphologies for a number of different languages. I'm pretty proud of that work. I think that it improved performance significantly. And it had some, it's efficient. It can be efficient, and it can be done without as much hand coding of rules as you might think. But there are other options when it comes to morphological analysis that you should be aware of. We're not going to talk about in great detail, but that are important. There are both unsupervised and supervised approaches to morphological analysis that are in practice. And the unsupervised ones are in some ways more interesting. So you can basically take a big corpus, feed it to Morphessor or Morphessor Flatcat, these unsupervised morphological learners, and get back a model that will parse words into morphemes. Now, it doesn't give you like a lexical form. It doesn't give you a lemma or a dictionary form, and it doesn't tell you what any of the other morphemes mean. It just gives you a segmentation. But this sometimes is enough, and this can be very useful. And it's much easier. It requires much less expertise and much less time to set it up. So, in certain problem domains, then this is the right solution. For English, there are pretty good morphologies that already exist that you can use, but they're proprietary. There are not a lot of good free ones. What there is that people use a lot for doing morphological things in English, which can be useful but should be used with care, are stemmers. Who here has used a stemmer before? Which stemmer to use? Quarter or snowball?
Snowball.
Snowball, okay. Can't remember. A stemmer. Anybody else? So what do you use a stemmer for?
Text classification.
Okay. So you're doing a text classification task, and you stemmed the words.
To reduce dictionary size.
Right. Right. You probably reduced sparsity of. It should have. So the stemmers can be useful. Basically, they're a way of doing morphology where you just lop off things at the end of a word through a cascade of regular expression replacements. So it's not as sophisticated as the kinds of things you can do with a finite state transducer, but they can be put together quite quickly and efficiently, and they run fairly efficiently too. And for when you don't care, so one thing, the stems that they produce, I don't know if you looked at the data, but the stems that they produce don't look like words. So if you need to be able to look up the result in some kind of lexicon or give it to a user or something like that, then a stemmer is not often the best option. But there are stemmers that are efficient, that are available for free, and that work fine for a lot of tasks. So you may, in your question answering task, be interested in using like Porter stemmer or Snowball stemmer, both of which are available in NLTK or some other stemmer. There are a number of other ones that are available for some of the work that you'll do in the project. Okay, let's switch to these other slides really quick. So these are some notes that the lead TA, Fatima, put together on evaluation metrics that should be relevant to the homeworks, because we're going to be using these kinds of evaluation metrics to evaluate your performance in the class. So it depends a lot on what task and what algorithm you're using, what evaluation metric you should use. So what kind of output are you producing? Is it a label, a binary decision, a real numbering, an order, a transformation of a text? And often there's more than one evaluation metric that could be used. So in the one project that I work on, then it's a DARPA-funded project, and NIST does the evaluations. And they're like, for the one task, they're like 10 different evaluation metrics. And they say one is primary, but it's not the one that makes us look best, so we say that another one is primary. So sometimes you evaluate to one, you optimize to one metric, but it hurts you on another metric. And so they're competing in nature. So here are some metrics for classification tasks. For rating tasks, we have AUC, ROC, area under the curve, discounted cumulative gain, precision at n, and so on. For regression, this MSE, RMSE. For association and agreement, we have things like Pearson's correlation or Cohen's kappa. There are distance and similarity metrics. So Hamming distance is one that we'll use in evaluating your first homework. Levenstein distance, cosine similarity. And then there are these, that's misspelled, blue. There are metrics for specialized tasks like blue and rouge. Word error rate is used in speech. For binary classification tasks, we have things like accuracy, precision, negative predicted value, recall, and F1. So what kind of task is the homework assignment in 1 and 2? Or homework assignment 1, task 1 and 2? So what are you doing? What are you doing, and what are you producing as output? Let's go back here. Yes.
Transforms text.
You're transforming text. So, what would you use to evaluate this? Transforming text. I mean, there are other ways of looking at the problem. I mean, you could look at it as kind of a degenerate classification problem where you're choosing whether each particular token should be anonymized or not. But various aspects of the task make it difficult to, the fact that you're overriding it rather than assigning a label makes it difficult to treat in that way. What kinds of metrics would be appropriate? Yeah.
Something like an edit distance.
So like edit distance. So we could use like Levenstein distance. We could use Hamming distance. What would be the difference between those two? This is foreshadowing next week. So Hamming distance basically assumes that the input and the output, or that the two, not the input and the output, but the two strings being compared are of equal length. And it just asks, are the corresponding elements equal or not equal. Love interesting distance allows for insertions and deletions. So they don't have to be of the same length, and it just measures how many edits, with usually an edit cost of 1 for insertion, deletion, and substitution. You know, so how many edits does it take to get from one string to the other? So which would you use? So which would be appropriate for these tasks? Yes.
I would say Levenstein would probably be better for task 1, and Hamming would be better for task 2.
What would you use Levenstein for task 1?
Because not all of the names that we're replacing have the same length as John Smith.
But you could do Hamming on a token level, though, rather than a character level.
Okay. Then yeah, that would make sense.
Yeah. So when might that produce unexpected results? If you use,
Sorry, can you explain what you mean Hamming on a token level?
so if you take Hamming over the words rather than over the characters, so you treat each word as if it's an element. Yeah. Does that make sense? So when might this give unexpected results? What happens if you change the number of tokens or the number of characters in the case of task 2?
You're breaking the assumption.
Right. So then you're trying to compute the Hamming distance between two sequences that are not of equal length. And so don't do that. Make sure you don't change the number of tokens or the number of, in task 1 or the number of characters in task 2. So any other arguments for using a different evaluation metric? What do you think? Yeah.
I think Levenstein could, you could have two words that are superficially similar. They're very different meaning-wise.
Mm-hmm.
And Levenstein would classify them as similar.
Right, if they're spelled similarly. Then. But Hamming would classify them probably as similar too. Just if they're
If you did it on like a word level, then
Mhm.
they would consider them similar.
yeah. Right. What else do you think? So if you were setting this up, what would you use as an evaluation metric? What do you think would be fair? What should we use as an evaluation metric to make you happy? We long to please.
It's a constant 100.
Then everybody else gets it 100. If you were us, what would you do? Okay, well, we'll use word error rate then. No. Just kidding. We thought about using blue for the first one, actually, which is blue is a metric that's used in machine translation. It basically measures how many shared n-grams there are between the two texts. And does everybody know what an n-gram is? Who knows what an n-gram is? So n-gram is like a sequence of n characters or n words. So for blue, it's n words. So a bigram is 2 words, a trigram is 3 words. So you just go over the whole text and find all the sequences of 2 words, all the sequences of 3 words, all the sequences of 4 words. And then you compare how many of those are shared between the two texts. And the more are shared, or the higher the blue score, basically. We decided not to do that. Okay, so we're going to use Hamming distance. You better make sure that you don't change the number of tokens in task 1 or characters in task 2. And then don't say we didn't warn you. You know, you had your chance to object. Now that we have settled this, we'll even get the Autolab script running. So, yeah, any questions about the homework, by the way? Yeah.
I have questions about using Hamming distance as a metric. Does that, if we handed in a script that did nothing, wouldn't that pass?
No.
Why not?
Like, because we're judging you against, if the script didn't change anything. So we're judging you against a reference. And so if we compare it to the reference, then the Hamming distance is going to be relatively large if you didn't do anything, because the reference is.
It's not just the count, it's like the count of matches for the what?
It's like the count of edits. So the number of, so if you line up all of the, so for task 1, if you line up all of the words in pairs, then every pair where the words are different is 1 demerit.
Okay. Cool.
Okay, all right, have a good day or evening or whatever it is.